So, so first, consistency. So consistency is a nice property that we saw for mom estimates. Basically, it says that that theta that the MLE converges in probability to the true parameter. So here's the picture I want you to hold on to. Essentially, looking at the MLE for different size samples, the distribution, it is a random variable. If you allow x1 to xn to be random, every different sample that you get a different MLE, right? You get a different value of the MLE. So we get distributions that become more and more concentrated at the true single value. It looks like 4 is the value of theta naught. So now the topic of consistency, in fact, MLE, can be a little bit technical because usually you have regularity conditions to assure that an MLE exists and that it is consistent. So the regularity conditions are that x1 xn is IID, so that the joint factorizes, that theta, so that the true parameter is an interior point, so that you can take a limit, and which you have in the definition of the derivative, that the log likelihood has a unique max, and also that the log likelihood's differentiable. Obviously, you're going to take the derivative and set it equal to 0, and that you can interchange the order of differentiation and integration. So under these regularity conditions, the MLE is consistent. So the book has a sketch of this. I rewrote that proof, and I also put in a picture so you can visualize what's going on with that. Take a look. I put it at the end of these notes. So let's start now with an exact calculation of the confidence interval for theta. So remember that a 95% CI for population parameter theta is an interval for which theta, which contains theta with certainty 95%. So an MLE estimator can provide us with an exact formula for 95% CI in very special circumstances. It really is the exception. So a 95% CI for the population mean and variance of a normal random variable is very popular. So we're going to give it here. So it will be in terms of the t distribution and the chi-square distribution. So we're going to need to give a little bit of background about those important distributions. So the chi-square distribution, I'm just going to define chi-squared with 1 degree of freedom as a gamma 1/2 distribution. It is, if z is standard normal, then z squared is chi-squared with 1 degree of freedom. So this fact is covered in Stat 134, but I actually proved this for you at the end of these notes in case you need it. So next I'm going to define what chi-squared with n degrees of freedom is. Chi-squared with n degrees of freedom, I'm just going to define it as gamma n over 2 1/2. And you can show, well, you know that z squared is gamma squared with 1 degree of freedom. So, I mean, it's chi-squared with 1 degree of freedom. And so independent gammas, the R parameter adds. So if you have n independent chi-squareds, you're going to get gamma n over 2 1/2. So the point about the degrees of freedom is that with chi-squared n degrees of freedom, you you have, it's the sum of n independent standard normals. Okay, so I'm to give you a little bit of insight into what this distribution looks like. Here is the graph of the distribution, and just notice it's a fact that the expectation of the chi-squared with n degrees of freedom is n, so that the center of the distribution shifts to the right as n increases. So now an important thing is that n minus 1 over sigma squared s squared, where s squared is the sample variance, is a chi-squared with n minus 1 degrees of freedom. So now I'm going to give an argument for this, and but I won't be able to prove it completely because it involves a very detailed moment generating function argument that I choose not to go into right now, but it is in Rice in chapter 6. But I'm going to give a sketch for it just so you can see what's going on. So first of all, note that 1 over sigma squared sum xi minus mu squared is a chi-squared with n degrees of freedom. But if you replace the mu by x bar, then it's going to be chi-squared with n minus 1 degree of freedom. It is plausible that you lose a degree of freedom there because although the xi minus mu are all independent, the xi minus x bar are dependent. So they're not going to be independent anymore, and you're going to lose some freedom there. But here's an argument. So it is. I think it's fairly understandable. Just algebraic steps here. N minus 1 s squared sigma squared. You can write that as the sum xi minus x bar over sigma, and you make a trick where you add mu over sigma and you subtract mu over sigma, and then let's call xi minus mu over sigma zi, and let's call x bar minus mu over sigma z bar, just to make the notation easier. Then you FOIL zi minus z bar, and you get what's shown here, which simplifies to sum of the xi squares minus n z bar squared. And so then we have the sum of the zi square is equal to n minus 1 s squared over sigma squared plus n z bar squared. The sum of the zi squares is a chi-squared with n degrees of freedom by definition, and the nz bar squared is a chi-squared with 1 degree of freedom because square root of nz bar is standard normal. So now comes the big guns that show that x bar and the sample variance are independent random variables when xi's are normal. So that's fascinating because you would not expect that, since x bar is actually in the definition of the sample variance. So you wouldn't expect they're independent, but when xi are normal, they are independent. So you can see Theorem A, page 195 in Rice, and I encourage you to follow that argument. You guys are responsible for knowing about moment generating functions. So it follows that n minus 1 s squared over sigma squared and n z bar squared are independent. And since the sum of independent gammas is gamma and the sum of xi squared is gamma n over 2 1/2, we conclude that n minus 1 s squared over sigma squared must be gamma n minus 1 over 2 1/2, which is chi squared n minus 1. So that shows that. So that's the end of what you need to know about chi squared. T distribution is another important distribution, so let's go over that. So it's defined as the ratio of a standard normal and the square root of chi squared over n divided by n. So that's the definition of a T distribution with n degrees of freedom. The degrees of freedom here just refer to the fact that u is a chi squared with n degrees of freedom. So the distribution of the ratio of z and the square root of u over n can be worked out and shown to have the following equation. It's this density here isn't something to remember. It just is interesting because if you look at the graph of that density, if you were to plot it, it almost looks like the bell curve. In fact, you can show that the T distribution converges in probability to the standard normal. That's quite interesting. You could even take a look at this density here and show that as n goes to infinity, you get the equation for the standard normal density. But I won't go through those details. So here we can see that the T distribution has fatter tails than the standard normal, which is in black. Great. So now x1 to xn is IID normal mu sigma squared, where mu and sigma squared are unknown. The T distribution comes up when we're making the confidence interval for mu. That's why we need it. So x bar has the sampling distribution, which looks approximately normal. The SD of this is the square root of sigma squared over n, which is, well, we don't know what sigma squared is, right? So that's approximately s over the square root of n. And now we're going to normalize x bar. So we get x bar minus mu over s over square root of n. And this is we're going to show this is a t n minus 1 distribution. So to show that, we just need to show that it's a ratio of z over square root of u n minus 1. And it's just an algebraic thing. You can see here that I can just write it that way. You can see there's cancellation, so that this equality that I'm highlighting right here is just, you can algebraically verify it. So this is all the knowledge about chi squared with n degrees of freedom and the T distribution that you need for this class. Just to finish up, let me show that, let's find the MLE for the parameters for the normal random variable. So what I've written out here is the likelihood for the normal, and I've written it as a product here because my x1 to xn are IID. Then here I've written, so here I'm writing the log likelihood, and then I take the partial derivatives and I set them equal to 0, and if you solve them, you get the it's no big surprise the MLE for the population mean is the sample mean, and you get that the MLE for the standard deviation is the square root of 1 over n sum xi minus x bar quantity squared. You can find by equivariance the MLE for sigma squared, and because that's just the MLE for sigma quantity squared. So that's 1 over n sum xi minus x bar quantity squared. And I just want to point out this is the same, the MLE estimator for sigma squared is the same as the MOM estimator. And furthermore, it's